All right, very good evening to all of you. Now, I got a lot of requests asking me about the December 2019 exam that happened in Assam and Meghalaya. That is the one that happened on 27 December 2019, right? And many suggested that those questions were quite new. So I thought I'll discuss a few questions, particularly from organic spectroscopy part. All right, there was one question from inorganic spectroscopy as well. That one also I have taken, right? So there were some interesting questions. The two markers were interesting, to be honest. The four markers were I found them to be easy, right? So let's have a discussion. It would be good for your revision as well. All right. So the first question, these are all two markers, right? First we'll discuss all the two markers. This question was that the correct order of chemical shift values of the methyl group protons in the following compound is. So we have to basically arrange them according to the chemical shifts. So there was one interesting part over here. So we have your nitromethane, okay. Then we have your nitrile, right? Acetonitrile over here. Then we have methyl chloride, and then we have this PHCOCH3, right? So if you see over here, if I write it down, if you like, there are 3-4 effects that come into the picture, right? We have the inductive effect, okay, generally on which the chemical shift values depend, right? Then we have the mesomeric effect, and then we have anisotropic effect, right? So these are the three effects that come into the picture. Now I had asked this question on my plus course as well, and majority of the students went with option number 3, okay, which is 1 2 3 4. And at the first glance it looks like that, because nitro group has a very high electron withdrawing effect. Then nitrile also has a strong electron withdrawing effect. Cl also has a strong withdrawing effect. And then the methyl over here. So they are asking the correct chemical shift of the methyl group, right? That means the CH3 group, this CH3 group, and like this, right? So over here, this CH3 is directly attached to a carbon, which is a carbonyl carbon, but obviously it is directly attached to a carbon, whereas in these three, it is attached to a Cl. Here also it is attached to a carbon, but a nitrile group is a very strong electron withdrawing group. So intuitively you might think that the answer is this, but there is one exception over here, okay. Now when I said anisotropic effect, now among these four options, nitro group shows an isotropic effect, and so does the nitrile group, okay. But the anisotropic effect of the nitro group is not that great, okay. And even if it is there, it will favor the methyl to come downfield, or to come at a higher chemical shift. But when we talk about nitriles are very similar to your alkynes. So like in alkynes also, what we say is that the electron density, like we draw a cone, generally we draw a cone like this, right? And the cone over here has delta negative charge, right? That means that the whatever protons are there in this particular region, they would see some shielding effect, okay. Shielding effect means they will come upfield, or they will come at a lower chemical shift, okay. They will come upfield. I hope you know the concept of upfield and downfield. So they will come upfield, okay. So if I draw this spectra over here, and let's say this is my ppm, and this is 0 and this is 10. So if a proton moves towards this side, we say it is moving downfield, and if it moves this side, we say it is moving upfield, right? So this is your upfield, and the other side is a downfield. So due to the shielding effect, the protons which come in this region of the nitrile group will be basically shifted upfield. Now fortunately, in this particular case, what happens is that the three protons of the methyl, they come in this shielded region, right? So even though you might expect these methyl protons to be highly de-shielded because of the presence of this nitrile group, which is electron withdrawing, but due to the anisotropic effect and due to this shielding effect caused by the anisotropy, what happens is this methyl protons are shifted upfield, okay. So what are the actual values? So if I write down the actual values over here, your methyl protons over here come at a value of 4.02. Your nitrile CH3CN actually comes at a value of around 1.9 ppm. Then we have CH3Cl at a value of 3.0 ppm, and then we have PHCOCH3, that is basically a carbonyl group which is attached to the methyl. It has a value of around 2.5, okay. So based on this, we can say that the answer is first 1, 3, 4 and 2, okay. 1, 3, 4, 2. So based on this, we can say that the correct answer is option number 2, 1, 3, 4, 2. So this was a little tricky question. You had to keep the anisotropy, you had to know about the anisotropic effect to get to this question. Otherwise you would have marked option number 3 like most of the students did. All right. So let's move to the next question. Okay. Yeah, the next question is based on your 13 CNMR, again a 2 marker. So this molecule that is given to us over here is called adamantane. Okay, I'll draw the structure over here for adamantane. I'll just enlarge the structure. Okay, so this is the structure of adamantane over here. Okay, now they had asked that in the proton decoupled 13C NMR. Decoupled means where the carbon atoms are not coupling with the hydrogens. Okay, that is what a decoupled 13C NMR means. It can sometimes be also written as 13C, and in brackets they can write 1H like this. That also means that it is a decoupled NMR spectra. Right? Sometimes they might write it, sometimes they would give it like that. So the number of signals observed in the proton decoupled 13C NMR spectrum of the following compound, which is adamantane, is what? Alright, so if you see over here, we have to see the different kinds of carbons that are present. Okay, those will be the number of signals that we'll get in the NMR. So if you see over here, I'll mark these carbons in blue, the ones that look similar. Okay, this carbon, and similarly this carbon also. This is these four carbons are similar. And let me take a yellow color, and let me mark the ones that I feel okay, yellow is not that great. Let's take magenta. So this um, this, okay, 1 2 and then 3 and then 4 5. Okay, so if you see this particular molecule, it has 6 7 8 9 10 carbon atoms, right? It has 10 carbon atoms. Am I missing some carbon atom? 1 2 3 4. Okay, I'm missing this one. So this one also would be blue. Yeah, so there are 5 blue, this one, right? So there are 5 you can say blue carbons, and there are 5 pink carbons or magenta carbons that I have marked. Now if you see their environment is exactly similar. Okay, you can you can see by yourself. This carbon has 2 hydrogens. I'll just give you one example. Okay, this carbon over here has 2 hydrogens, and this two hydrogen carbon is next to a carbon which is pink, magenta or pink in color, and next to another carbon which is blue in color. Okay, similarly, if you go for this particular carbon over here, sorry, this again I've done some I marked it incorrectly, very sorry. Let me just do this again. I've done the markings incorrectly, right? And then this will also be magenta, and then this will be blue, this will be blue, and this will be blue, right? So this will be the marking. So you can see over here that this blue carbon that I've marked is next to 2 magenta carbons, or adjacent to 2 magenta carbons, and 1 magenta carbon is adjacent to 2 blue carbons, right? So similarly you can check out the environment over here. So these blue carbons have the same environment, and these magenta carbons have the same environment. So you'll only get 2 peaks in the proton NMR, or sorry, in the 13C NMR for this particular carbon, right? You can check it out by yourself also. So this was an easy question. You just needed to decipher it correctly. Okay, this was not a tricky question. The first one I can still say was a bit tricky, but this was a easy question. So let's move forward to the next one. Now the next question says that the correct order of CO stretching frequency in the following compounds is, and these are the 3 compounds given. Okay, so all of you know that whenever you are preparing for CSIR net, you should know the stretching frequencies of various carbonyl groups. Okay, so over here this is a bit tricky. How it is tricky, I'll just tell you. So this over here is basically a carbonyl attached to oxygen. Okay, so basically the stretching frequency, you can say it's like a ester group, right? So the stretching frequency for this particular ester groups is around 1740, right? Around 1740 centimeter inverse. Okay, so for one I will get a value of around 1740 centimeter inverse. If I look at this particular molecule, this is like it has a simple carbonyl moiety or a ketone, right? So for this roughly the value will range around 15 centimeter inverse for ketones generally. Now, if you look over here, this is a simple carbonyl, and at a very far distance we have a NH group. Okay, at a very far distance we have a NH group. Now, you might think that this nitrogen over here, since it's an electronegative atom, it would pull electrons towards. It will pull electrons from this carbon, even though the effect would not be that far. Like the effect of this nitrogen would not go that far, but still you might wonder that okay, this nitrogen is electronegative, so it might pull some electrons. So the the stretching frequency of this carbonyl bond might increase because of the increase in the polarity difference. Okay, if the polarity difference increases, that means this carbon becomes more delta positively charged and this becomes more delta negative, so the polarity difference will increase, so the bond strength will increase, right? So based on that, you might be thinking that this will have the highest stretching frequency, ester group, and then we would have 3, and then we would have 2, so you would be going with 1 3 and 2. Okay, you might go with third option, but it would come out to be incorrect. Okay, why in this case that is not happening? The explanation that I gave. See, in this particular case, in the third case, if I draw the molecule, what exactly is happening is something called as a transannular effect. Okay, transannular effect. Okay, so what happens is, this is given in two books, this effect. Okay, one is in Culsey, it is given in PS Culsey. Okay, you can find this effect in that book, and also there's one more book on stereoelectronic effect. So in both these books it is given that for a medium sized ketone, okay, or for a highly flexible ketone group, what happens is this nitrogen sometimes comes in the correct orientation to donate its electrons to this carbonyl. Okay, it donate its electrons to this carbonyl carbon. So in turn what happens is it acts like a amide bond. Okay, instead of acting as a carbonyl bond, it starts acting as a amide bond, and this is known as transannular electron donation. Okay, a lot of research papers have also been recently published on this effect, even though it is established a long time back, but still now even a lot of research papers are being published on this topic, right? So this is called as transannular electron donation. Okay, transannular, you can read about it, it's given in PS Culsey. So basically what happens is it what in summary what I would suggest is that it acts as a amide bond. So the amide bond, you know, has a stretching frequency of roughly around it can go up to 1650 also, but generally we say it is around 1690 centimeter inverse. Okay, it could be lower also. So for this molecule, I think it is around 1690 centimeter inverse. So basically it acts like a amide bond in summary. So we have a ester which will have the highest stretching frequency, followed by a ketone, and then you can say that this, due to the transannular electron donation, this one acts as a amide. So the correct answer would be first option, that is 1, 2 and 3. All right, so again this was not a direct question, it was a bit tricky. So let's move forward to the next question. So these were all the your 2 markers. So for 1 2, so there were 3 2 markers. Okay, now let's go to 4 markers. There were four 4 markers from spectroscopy, organic spectroscopy part, right? The first one that we have is this one. So this is a bit like this the explanation is a bit lengthy, so let's move on to the other 2 ones before coming to this one. So this was a simple question from mass spectrometry, and you would have seen there was a mass spectrometry question in the 15 December 2019 exam as well. Okay, so both of these questions were quite simple from mass spectrometry, and over here the question says that the base peaks for isomers A and B in the mass spectra are due to the following ionic species. Okay, so basically you have to identify the base peak, and the base peak would be there because of which ionic species. So it's a very general thing. Even if you have studied mass spectrometry superficially, you would know that, you know, phenyl groups which have a alkyl group substituted on them, they generally lead to formation of tropylium ion. Okay, so how tropylium ion gets formed is, for example, let's say if I have a phenyl group and I have CH2, and then I have some R group. Okay, it could be alkyl group or whatever it might be. So what happens is that when I in mass spectrometry, when I bombard it with electrons, okay, when I bombard it with electrons, what happens is this bond over here, let me mark it in red, this bond over here cleaves. Okay, so once this bond cleaves, what do you get? You get this kind of intermediate. Okay, you get this kind of intermediate. Okay, your radical ion is formed, and once this is formed, immediately what happens is immediately it converts into this form. Okay, a 7-membered ring. um, okay, and we have a double bond here, a double bond here, and a positive charge. 1 2 3 4 5 6 7. Okay, yeah, so it forms this intermediate which is called as a tropylium ion. Okay, this is a tropylium ion, and all of you can see that it is stabilized by resonance. Okay, by your aromaticity, it's aromatic in nature, so it's basically stabilized by your aromaticity, right? And that is why, you know, it gets converted into your tropylium ion. Okay, so this basically this intermediate whatever is formed, that gets converted into tropylium ion, and its M by Z value is around 91, I think. Okay, I'm not sure, 97 or 91, I think 91. Okay, we have 7 carbons, so 7 into 12, that is 72, and then if you include the hydrogens, I think it will come out to be equal to 91. All right, so it's equal to 91 as M by Z. I'm not sure, you can just confirm. So So what is the base peak? I hope you know that the base peak is the most intense peak in the mass spectra. That means the peak that is highly stabilized. So all of you know that because of the aromatic character, this tropylium ion is highly stabilized. So generally it comes as a base peak. Now both these molecules are very similar, okay, but the only difference is, like in the B molecule, what will happen is this here the cleavage, sorry, not here, very sorry, the cleavage will take place over here. So you will get the tropylium ion because of, you know, a radical anion will be formed similar to this one. Similar to this one, a radical cation will be formed, and then it will lead to the formation of tropylium ion. But in B, what will happen is this will cleave. Okay, the cleavage of the bond will take place from this side. So what will happen is that we would get this molecule. Okay, we'll get a radical cation over here. Okay, we will get a radical cation at this position, but we'll also have a methyl. So once the tropylium ion is formed, once the tropylium ion gets formed, okay, so what will happen is that the tropylium ion will form, but will also have a methyl group attached. Okay, so it will form something like this, which is given in option number 4. Okay, so the correct answer for this was option number 4. Okay, the explanation was maybe a little lengthy, but the question was very simple. Okay, it was not a difficult question at all, even if you had a glance at the mass spectrometry. Okay, in mass spectrometry there are 2 or 3 important topics. So one of the most important topics is McLaughlin rearrangement, on which a lot of questions are asked. Then the second most important topic is your isotopic abundance. Okay, a lot of questions are put up from mass spectrometry based on isotopic abundance as well. All right, so let's move on to the next question. This is basically from inorganic spectrometry, spectroscopy, but you can still do it. It's very simple and easy to understand. So in the 31p NMR spectrum of P4S3, okay, the structure was not given to us. Okay, I've drawn the structure over here for convenience, but the structure was not given to us. It is given that your 31p p has a, spin value of half, whereas your sulfur does not have any spin value. Okay, so your sulfur is NMR inactive, and you have to just tell in the 31p NMR spectrum how many number of peaks or how many number of signals you will obtain, and what will be the splitting pattern. So this is very simple. First of all, you should know the structure of P4S3. Okay, and I'm sure that if you are preparing for CSIR net and you are doing inorganic chemistry, P4S3 has been asked a number of times in the exam, but different kinds of questions have been framed from it, right? So like sometimes they ask you the number of PP bonds and the number of phosphorus sulfur bonds in P4S3. Now this time they have asked based on the structure, the NMR. So if you know the structure, you would have drawn this. And if you look at the structure, we have 2 different types of phosphorus. Okay, sulfur is inactive, so we don't have to consider that. But if you look at the phosphorus, there are 2 different kinds of phosphorus. One is this one. Okay, the one I have marked in red. This is in a different environment. And let me mark the others in green or blue. Okay, let me mark the others in blue. So this one, and this one are in the same environment. You can check it out. You can see how they are bonding to the other atoms, and you will see that all these 3 phosphorus that I marked in blue are in one environment, and the one that I marked in red is in another environment. So what will happen is, since their I value is half, so basically the splitting pattern will be same as that for proton. Okay, the splitting pattern will be same as that of proton. So for this phosphorus, we have 3 different phosphorus. Okay, 3 different phosphorus. So basically we can use the 2Ni plus 1 rule. So 2 into number of phosphorus are 3, and spin value is half plus 1. So they basically 2 gets cancelled out. It will split into a quadrat. So these 3 phosphorus will split the red phosphorus into a quadrat. Okay, it will split it into a quadrat. Similarly, the red one, what it will do, since it's only 1 in number, so again 2 into n value is 1 into half plus 1, so 2 gets cancelled. So it will split all these 3 phosphorus, the ones in blue, into doublets. Okay, it will split it into doublets. So we'll get one signal which will be a quadrat, and we'll get one signal which will be a doublet. So if you look at the two of the all the options, option number 1 makes the most sense. We'll get 2 signals, one for this phosphorus in red and one for these 3 phosphorus in blue, and the signals will be a doublet and a quadrat. Okay, they could have also asked you the intensity or the integration pattern also. So this signal, the one which will be a doublet, because it is happening because of 3 phosphorus, so it will be 3 times greater than the one which will be a quadrat, which will happen due to 1 phosphorus. Okay, so they did not ask you that, but there is some additional information when you're solving something. All right, so these were the 4 markers, and one 4 marker we had missed out. So let's discuss that. that was based on organic spectroscopy. So the question says that the proton NMR is given to us, and these are the four options. Okay, so first of all, what strategy I generally recommend is, first of all, you look at what are the different structural features in all these four molecules. So the first structural feature you will see is that over here we have this hydrogen in all the three options, which will basically come as a singlet. Okay, more or less come as a singlet. Whereas in this particular fourth option, you can see all hydrogens are adjacent to each other, so they will all split each other into different splitting patterns. So you will not observe a singlet. So you check in the aromatic region if you are getting a singlet or not. So if you look at the aromatic region, this 6.28, 6.35 and 6.98, these are the protons in the aromatic region. I generally don't recommend referring to mass spectrometry, because generally you can solve questions without the help of mass spectrometry also. There was only one exception, that in your June 2019 examination, there was a question of 4 marks which you could not solve without the help of mass spectrometry. Otherwise, generally you are able to solve it without the help of mass spectrometry. All right. So you see that in the aromatic region, we do have a singlet. Here we have a singlet. So that means immediately you can cancel out option number 4, because you will not observe any singlet in option number 4. Okay. Now among the first, second and third option, there's not a big structural difference. Okay, one structural difference that you would see is that here we have a simple NH2. Okay, and here we have a NH2 which is basically attached to aromatic ring. Okay, and then here we have a amidic NH2. Now there is a difference in the chemical shift values for a amidic NH2, for a NH2 which is attached to aromatic ring, and for a NH2 which is simply attached to aliphatic group. But the problem is that in different kinds of NH2 peaks or even OH proton, the chemical shift for a OH proton and the chemical shift for NH protons, they vary a lot with the solvent that you are using. Okay, like for example, if I'm using a polar solvent, their values will be different. If I'm using a non-polar solvent, their values might vary. Okay, so it is never reliable to judge the answer based on the chemical shift values of the NH proton or the OH proton. Okay, so you always have to look for alternative strategies. All right, and here you know that the value is given to you as 4.00, which is given as a broad singlet. Okay, so whenever you see this term broad, that only happens for acidic protons like your OH or NH protons, right? And since the value is given as 4, I know that the answer is option number 2, but I will have to confirm it. Okay, because like I said, that it depends on the polarity of the solvent in which you are performing the NMR also. All right. Generally, I'll just tell you for your recommendation that if you have amidic NH2 like this one over here, this proton values generally come around 7. If you have aromatic NH2 like this one over here that we have, this one comes around 4.5 to 5.5 generally. And then the simple NH2 which is attached to aliphatic groups, you see in the region of 2 to 3 generally. Okay, but again, this is just for your reference. Never rely on the acidic protons chemical shift values. All right, so now what is the next thing that we can do? So the next thing that we can do is, let me just erase this off again. So the next thing that we can do is, if you look at this bond, this is amide. Okay, similarly here also you can say this is like a amidic bond. Okay, so in general, even though they are not very strong electron withdrawing groups, but they are electron withdrawing in nature. But NH2 over here is a strongly electron donating group. So the next thing that we see is, or when I was talking about the chemical shift values of the aromatic protons, immediately I observed something very peculiar. What did we observe? That this is value at 6.2, this is at 6.3, and this is at 6.98. So these values correspond to a very shielded aromatic protons, very highly shielded aromatic protons. That means these aromatic protons somehow have very high electron density associated with them. Now if I talk about this amide, because generally aromatic protons come at a value of 7.2. Now, if I talk about these amidic, amidic bonds over here that are there, these carbonyl which is amidic in nature. So what is happening over here? They are still electron withdrawing. They cannot donate electrons. Okay, even though their electron withdrawing effect would not be that great, but they are not becoming electron donating in nature, right? So this the kind of chemical shift that we are obtaining, that basically associates with a strongly electron donating group. Okay, so based on that, we can say that the option number 2, because you can see that the singlet that we are getting is at 6.35. So this one would be at around 6.35, or let me just draw it fresh so that you can see it more clearly. Like we have this some R group over here, and then we have a NH2 over here. Okay, so this one at 6.35 is the singlet that we are getting, and then you are getting another one at basically 6.28. So at 6.28 basically it will be this proton, which is basically have, because NH2 has a ortho para directing group. Okay, it's a ortho para directing group, so it will increase the electron density at this hydrogen. But also, since it's a due to the minus I effect, it will also have minus I effect. So it will have plus M effect and minus I effect. So due to this minus I effect, it will still have some electron density withdrawn from this hydrogen. But since it's orthopara and the minus I effect will not be significant at this position, so you can see that this value is even more upfield. Okay, at 6.28, it is more upfield at a value of 6.28. That means it has even higher electron density, because the plus M effect is at full power, but the minus I effect is not able to reach at that position, right? So based on this analogy, or on based on this strategy, we can say that the correct answer is option number 2. So like I said, that the 4 markers from your CSIR net December 2019, the Meghalaya and Assam exam, were not difficult, but yes, the 2 markers were tricky. And if I talk about the overall examination was a bit tough when you compare it to the exam that happened on 15th of December throughout India, right? So I hope this video was helpful to you. If you want more such videos, more such practice questions, it's easier for me to make, right, rather than the concept videos, because they take a lot of time. So in case you like it, give this video a big thumbs up, and do subscribe to the channel. And also, like I said, if you like this kind of this kind of videos, just let me know down in the comment section, right? So thank you so much for watching. I do not make any edits. Okay, so in between you would see little hiccups, but that's because a lot of time is wasted doing editing, so I generally don't prefer doing editing, right? So please bear with that, right? Thank you.